The Mitsubishi A6M Zero dominated the Pacific skies with a remarkable during the early years of World War II. This legendary Zero fighter plane combined exceptional range, maneuverability, and speed in ways that seemed to defy the engineering limitations of its era. The Japanese Zero fighter represented a masterpiece of aviation engineering, achieving performance metrics that left Allied pilots and engineers in disbelief. The Mitsubishi Zero Plane's revolutionary design pushed the boundaries of lightweight construction, aerodynamics, and systems integration. Its Nakajima Sakae engine, coupled with advanced structural engineering, created an aircraft that could outmaneuver any opponent while maintaining an operational range exceeding 1,900 miles. This video examines the groundbreaking engineering decisions, innovative materials, and technical compromises that made the A6M Zero one of history's most significant fighter aircraft. From its ultra-lightweight construction to its advanced aerodynamic features, every aspect of the Zero's design reveals remarkable engineering ingenuity, revolutionary lightweight design philosophy. At the heart of the Mitsubishi Zero's engineering excellence lay a radical lightweight design philosophy that challenged conventional aircraft construction methods of the 1940s. Chief engineer Jiro Horikoshi's team embraced weight reduction as their ultimate objective, implementing innovative solutions that would define a new era in fighter aircraft design. The Zero's engineering team achieved remarkable weight efficiency through meticulous attention to detail. They crafted complex brackets from sheet aluminum with strategic lightning holes instead of using larger, heavier metal pieces. The A6M Zero weighed just 5,555 pounds, making it 1,871 pounds lighter than its primary adversary, the Grumman F4F4 Wildcat. Key weight-saving innovations included the use of plywood reinforcements in select areas instead of metal, strategic placement of the engine close to the cockpit for better weight distribution, and permanent wing-to-fuselage joining to reduce structural components. The cornerstone of the Zero's lightweight construction was the revolutionary Extra Super Duralumin (ESD) developed by Sumitomo Metal Industries in 1936. This zinc aluminum alloy offered superior strength-to-weight ratio, enhanced fatigue resistance, and greater ductility compared to contemporary materials. To counter ESD's vulnerability to corrosion, engineers developed an innovative zinc chromate anti-corrosion coating. This solution preserved the material's lightweight properties while ensuring structural integrity. The Zero's structural design represented a masterclass in engineering efficiency. The wing loading was kept at just 24.3 lb-2, significantly lower than the Wildcat's 28.6 lb-2. This reduced wing loading, combined with the aircraft's lightweight construction, enabled exceptional maneuverability at speeds below 60 knots. The engineering team implemented several groundbreaking structural solutions, such as the integration of the wings directly to the center fuselage, simplified tail assembly mounting behind the cockpit, and strategic placement of control surfaces for optimal weight distribution. The design's emphasis on weight reduction came with trade-offs. The absence of pilot armor and self-sealing fuel tanks made the aircraft vulnerable to enemy fire. However, these compromises aligned with the Japanese naval doctrine of the time, which prioritized offensive capability and maneuverability over defensive features. The Zero's wing structure utilized two main spars with continuous eye sections running from tip to tip, constructed using T-section extruded caps joined by a solid vertical web. This innovative approach created a robust yet lightweight framework that supported the aircraft's exceptional performance characteristics. Advanced aerodynamic features. The aerodynamic mastery of the Mitsubishi Zero fighter plane showcased Japanese engineering prowess through its innovative wing design and sophisticated control systems. The aircraft's aerodynamic configuration represented a significant leap forward in naval aviation technology of the 1940s. The Zero's low-wing cantilever monoplane layout incorporated a high-lift, low-speed wing design that achieved remarkable performance metrics. With its wing loading at just 24.3 lb-2, significantly lower than the Grumman F4F4 Wildcat's 28.6 lb-2, the aircraft could maintain controlled flight at speeds below 60 knots. The inverted gull-wing design served multiple purposes, allowing for shorter landing gear while minimizing aerodynamic drag. The Japanese Zero fighter's exceptional performance relied heavily on advanced drag reduction methods. Key aerodynamic features included flush riveting throughout the airframe, streamlined cockpit canopy with excellent visibility, smooth wing-to-fuselage integration, and aerodynamically optimized engine cowling. The aircraft's construction methodology prioritized aerodynamic efficiency, with the fuselage and wings built as a single unit rather than separate components. This unique approach, though slower in production, resulted in superior structural integrity and enhanced close-range maneuverability. The A6M Zero's control surface design balanced maneuverability with pilot control. Early models featured servo tabs on the ailerons to address pilot complaints about heavy control forces at speeds above 300 km/h. The engineering team developed an elastic control system with thin elevator cables that stretched slightly as speed increased, complemented by a flexible elevator control torque tube. The Zero's ailerons were specifically engineered to be large and powerful, contributing to its exceptional low-speed maneuverability and impressive roll rate. However, this design choice resulted in increased control difficulty at higher speeds, a trade-off that aligned with Japanese naval combat doctrine, emphasizing close-range dogfighting capabilities. The Mitsubishi Zero Plane's control surfaces demonstrated remarkable engineering ingenuity in managing the aircraft's broad speed envelope, which ranged from low-speed maneuvering to speeds exceeding 300 mph. This versatility in control response across different flight regimes distinguished the Zero from its contemporaries, though it came with operational limitations at higher speeds. Powerplant integration engineering. The powerplant integration of the Japanese Zero fighter represented a crucial engineering challenge that demanded innovative solutions to balance performance with weight constraints. The selection and modification of the engine would prove vital to the aircraft's legendary status in aviation history. The development of the Zero's power plant was a critical factor in the aircraft's evolution, enabling it to maintain its reputation as one of the most formidable fighters of its era. Initially, the Zero was powered by the Mitsubishi Z13 engine, which delivered 780 horsepower. While this engine provided a solid foundation, the real transformation occurred with the introduction of the Nakajima Sakae series engines, which significantly enhanced the aircraft's performance and capabilities. The first major upgrade came with the A6M2 variant, which utilized the Nakajima Sakae 12 engine. This 14-cylinder radial engine, arranged in 2 rows, generated 925 horsepower and featured a supercharger for improved high-altitude performance. Additionally, the engine incorporated a 1.71:1 gear reduction system, which optimized the propeller's efficiency and contributed to the aircraft's excellent speed and maneuverability. As the Zero continued to evolve, later variants saw further advancements in engine technology. The A6M3 model was equipped with the Nakajima Sakae 21 engine, capable of producing 1,130 horsepower, providing a noticeable boost in power. This engine not only enhanced the Zero's speed and climb rate, but also allowed for improvements in overall performance. The A6M5 variant introduced refinements to the Sakae 21 engine, including improved cooling systems, which addressed issues of overheating during extended operations and further increased the aircraft's reliability. The experimental A6M6 model marked another leap forward with the inclusion of the Nakajima Sakae 31A engine. This advanced power plant incorporated a water methanol injection system, enabling it to reach an impressive output of 1,210 horsepower. Although this variant did not see widespread production, it demonstrated the potential for even greater performance in the face of evolving aerial combat demands. Through these incremental advancements in powerplant design, the Zero maintained its competitive edge, balancing power, agility, and reliability to remain a potent force in the skies throughout its service life. The Mitsubishi Zero's cooling system showcased exceptional efficiency, reflecting the ingenuity of its engineering design. The engine cowling was a particular highlight, offering effective cooling for the aircraft's 14-cylinder radial engine while maintaining a compact intake that contributed to the Zero's streamlined profile. This balance between functionality and aerodynamics was critical to the fighter's success. The cooling system evolved alongside the Zero's power plants, with engineers introducing refinements to address the specific challenges of each engine variant. The early Sakae 12 engine featured a compact cowl design that provided adequate cooling while minimizing aerodynamic drag. This innovation ensured that the aircraft retained its agility and speed without compromising engine performance. With the introduction of the Sakae 21 engine, engineers enhanced the airflow system to improve cooling efficiency, particularly at higher altitudes where thinner air posed additional challenges. This upgrade bolstered the engine's reliability and allowed the Zero to perform more effectively in high-altitude combat scenarios. The experimental Sakae 31 engine incorporated a water methanol injection system, which represented a significant advancement in temperature management. This innovation not only allowed the engine to operate at higher power levels, but also ensured stability during demanding flight conditions. Each iteration of the cooling system played a crucial role in maintaining the Zero's competitive edge, demonstrating a commitment to continual improvement in both performance and engineering excellence. The A6M Zero fighter's power-to-weight ratio remained a crucial advantage throughout its operational life. The initial design achieved 0.454 horsepower per kilogram, significantly higher than contemporary fighters. This optimization came through careful engine placement and weight distribution, with the power plant positioned to maintain the aircraft's center of gravity. However, this emphasis on lightweight design created limitations. When more powerful engines were considered, extensive redesign became necessary to maintain the aircraft's balance. The installation of heavier power plants required moving the engine closer to the bulkhead, which reduced fuel capacity and combat radius. Despite these challenges, the Japanese Zero engine maintained its performance advantage through careful engineering compromises and continuous refinement of the Sakae series engines. The Zero's power system integration represented a delicate balance between competing demands. While American engines of the period were achieving significantly higher power outputs, the Zero's engineering team focused on optimizing their more modest power plant through superior aerodynamics and weight reduction. This approach proved highly effective during the early war years, though it would eventually become a limitation as more powerful Allied fighters entered service. Combat performance engineering. Engineering combat performance into the A6M Zero required careful balancing of seemingly contradictory requirements. The Japanese Navy demanded exceptional maneuverability while maintaining unprecedented range capabilities, pushing the boundaries of 1940s aviation technology. The Zero's legendary maneuverability stemmed from sophisticated engineering choices. At speeds below 4,500 meters altitude, the aircraft demonstrated exceptional turning capabilities. The engineering team achieved a remarkably tight turning radius of 1,118 feet, while maintaining 186 mph airspeed after a 180-degree turn. Key maneuverability features included low wing loading at 24.3 lb VF2 compared to the F4 Wildcat's 28.6 lb VF2. Optimized center of gravity placement near the cockpit. Advanced control surface design for enhanced responsiveness. Range engineering represented one of the Zero's most significant achievements. The aircraft could achieve an operational range of 1,900 miles, far exceeding contemporary fighters. This exceptional performance was achieved through a combination of innovative fuel storage solutions and meticulous airframe design. The Zero's internal fuel capacity of 150 gallons provided a base range of approximately 1,200 miles, a substantial distance for a single-engine fighter. To extend this range even further, engineers incorporated an additional drop tank with a capacity of 94 gallons, which added another 800 miles of operational reach. The engineering team achieved this range while maintaining maneuverability by positioning fuel tanks close to the aircraft's center of gravity and implementing weight-saving measures throughout the airframe. The speed-weight relationship presented complex engineering challenges. While the A6M Zero maintained a better power-to-weight ratio than the F6F5 Hellcat, it achieved a lower top speed. This trade-off resulted from several engineering decisions. The aircraft demonstrated optimal performance at speeds below 288 knots at 4,500 meters, above which the ailerons stiffened significantly. This limitation stemmed from the fundamental design philosophy prioritizing maneuverability over high-speed performance. The engineering team's decision to forgo armor protection and self-sealing fuel tanks reflected their focus on achieving optimal performance through weight reduction rather than protection. These engineering choices proved highly effective in early war operations, achieving an initial air-to-air kill ratio of 12:1. However, as the conflict progressed, the limitations of these trade-offs became apparent. The Zero's inability to maintain performance in high-speed dives and its vulnerability to battle damage highlighted the consequences of prioritizing maneuverability and range over structural robustness. Materials science innovations. Materials science breakthroughs played a pivotal role in the A6M Zero's exceptional performance characteristics. The development of innovative alloys and composites enabled Japanese engineers to push the boundaries of aircraft design during the 1940s. The cornerstone of the Zero's material innovation was the groundbreaking Extra Super Duralumin (ESD), developed by Sumitomo Metal Industries in 1936. This revolutionary aluminum alloy achieved unprecedented strength-to-weight ratios through zinc alloying with aluminum. The material demonstrated three crucial properties: include superior strength compared to contemporary alloys, enhanced ductility for complex forming operations, and significantly reduced weight while maintaining structural integrity. However, ESD's susceptibility to corrosion presented a significant challenge. Engineers addressed this through an innovative zinc chromate anti-corrosion coating applied post-fabrication. This protective layer preserved the material's exceptional properties while ensuring longevity in maritime operations. The Zero's structural design incorporated various composite materials strategically placed throughout the airframe. Material selection focused on optimizing the strength-to-weight ratio, with different components utilizing specific composites based on their structural requirements. The fore fuselage, which bore the greatest stress during flight and combat, was crafted from .048-gauge alloy. This material provided enhanced structural strength, allowing the aircraft to withstand the rigors of high-speed maneuvers and the impacts associated with its role in aerial engagements. For the upper section of the airframe, engineers utilized a slightly lighter .035-gauge alloy. This choice reduced the overall weight of the aircraft without compromising its ability to maintain structural integrity under normal operating conditions. The aft section of the Zero, where structural demands were less critical, featured an even lighter .018-gauge alloy. This material was chosen to maximize weight savings, contributing to the aircraft's exceptional agility and long-range capabilities. The engineering team employed innovative riveting techniques, utilizing rivets as small as 1/32" in diameter. This approach maintained structural integrity while minimizing weight and aerodynamic drag. The Zero's materials underwent rigorous stress analysis to ensure reliability under combat conditions. Engineers implemented comprehensive testing protocols that examined fatigue resistance under repeated loading cycles, structural integrity at varying altitudes and temperatures, and impact resistance and material degradation patterns. The success of these material innovations influenced post-war aviation significantly. The American aluminum industry, recognizing ESD's superior properties, developed a similar 7075 alloy in 1943. This material would become a standard in aircraft construction, demonstrating the lasting impact of the Zero's material science breakthroughs. The structural testing methodology proved particularly innovative, with engineers developing new techniques for analyzing material behavior under combat conditions. The Zero's construction utilized flush riveting throughout, with fore and aft joints being lapped and others butted. Despite using smaller rivets than contemporary aircraft, extensive testing confirmed the design's structural integrity. Production engineering challenges. Production engineering of the A6M Zero presented unique challenges that pushed the boundaries of 1940s manufacturing capabilities. The demanding requirements for lightweight construction while maintaining structural integrity required innovative approaches to aircraft assembly. The production of the Japanese Zero fighter demanded extraordinary attention to detail in manufacturing. Workers crafted complex brackets from sheet aluminum with precise lightning holes, choosing labor-intensive processes over simpler but heavier alternatives. The manufacturing team developed specialized techniques for joining subassemblies, with wings, fuselage, tail, engine, and landing gear following separate production paths before final integration. One of the most innovative approaches in the Zero's construction was the permanent joining of the wings to the fuselage. This method reduced structural weight and enhanced the aircraft's durability by eliminating the need for additional fasteners and reinforcing materials typically required in detachable designs. Additionally, the manufacturing team strategically incorporated plywood reinforcements in specific areas of the airframe, an unconventional choice that provided localized strength while maintaining overall weight efficiency. The use of advanced sheet metal forming techniques further highlighted the ingenuity behind the Zero's production. Workers shaped aluminum with precision, creating components that featured intricate lightning holes designed to minimize material usage while preserving essential strength. This combination of innovative techniques and painstaking attention to detail not only resulted in an aircraft with remarkable capabilities, but also demonstrated the extraordinary craftsmanship and engineering expertise of its creators. Quality assurance for the Mitsubishi Zero Plane required rigorous testing protocols. The engineering team implemented comprehensive inspection procedures for critical components, particularly focusing on the aircraft's unique structural elements. The manufacturing process demanded exceptional precision, as demonstrated by the complex bracket assembly supporting the aileron control tube. The quality control system emphasizes important things like detailed inspection of lightweight components, verification of structural integrity, testing of control surface assemblies, and material strength validation. Resource management proved crucial in the Zero fighter plane's production. The manufacturing team developed innovative approaches to material utilization, particularly in working with the advanced extra super duralumin alloy. This lightweight material required special handling and precise manufacturing techniques to maintain its structural properties. The wing assemblies exemplified the efficient use of materials through integrated construction techniques. This approach minimized material waste by reducing the need for redundant components and allowed the wings to maintain their strength while remaining lightweight. Similarly, the control surfaces of the aircraft were crafted with precision fabrication processes that not only conserved resources but also optimized labor efforts, ensuring that production goals were met without compromising quality. The fuselage structure, another critical element, was constructed using modular assembly methods. This strategy improved manufacturing efficiency by streamlining the production process and facilitating the integration of subassemblies. The A6M Zero's production process demonstrated remarkable efficiency despite its complex requirements. The aircraft's gross weight of 5,555 pounds, achieved through careful manufacturing processes, was 1,871 pounds lighter than the Grumman F4F4 Wildcat. This weight reduction required precise manufacturing tolerances and innovative assembly techniques. The production engineering team faced significant challenges in maintaining quality while meeting increasing demand. They developed specialized processes for working with the zinc chromate anti-corrosion coating, which required careful application after fabrication to protect the lightweight alloy structure. This coating process became a critical step in ensuring the aircraft's durability in maritime operations. Manufacturing efficiency was achieved through careful optimization of production flow. The team developed innovative approaches to joining subassemblies, with the aft fuselage including the tail designed for efficient mounting to the forward fuselage at a point just behind the cockpit. This modular approach streamlined production while maintaining the aircraft's exceptional performance characteristics. The Japanese Zero engine installation required precise manufacturing processes to achieve optimal weight distribution. The production team developed specialized techniques for mounting the power plant close to the cockpit, which not only saved weight, but also enhanced the aircraft's maneuverability. This engineering decision required careful attention to manufacturing tolerances and assembly procedures. Systems integration. Systems integration in the A6M Zero represented a complex orchestration of weapons, fuel, and control systems working in harmony. The integration challenges demanded innovative solutions that would define the aircraft's combat capabilities. The weapons integration strategy for the Japanese Zero fighter balanced firepower with weight constraints. The standard armament configuration included two 7.7 machine guns in the fuselage and two 20 mm cannons in the wings. This arrangement provided effective coverage while maintaining the aircraft's exceptional maneuverability. The weapons system design prioritized synchronized firing mechanisms for fuselage-mounted guns, wing-mounted cannon placement for optimal weight distribution, and ammunition feed systems designed for minimal interference with control surfaces. The fuel system engineering of the Mitsubishi Zero Plane achieved remarkable efficiency through innovative design. The internal fuel capacity of 150 gallons, combined with a 94-gallon drop tank, enabled an operational range of 1,900 miles. This exceptional range capability stemmed from the careful integration of fuel tanks near the aircraft's center of gravity. The absence of self-sealing fuel tanks, while increasing vulnerability, significantly reduced weight and contributed to the Zero's exceptional performance characteristics. This engineering trade-off aligned with Japanese naval doctrine prioritizing offensive capabilities over defensive features. The A6M Zero fighter's control system demonstrated a sophisticated integration of mechanical and aerodynamic elements. The control surface design featured innovative solutions to address pilot feedback about heavy control forces at high speeds. Engineers introduced an elastic control system that utilized thin elevator cables, carefully designed with specific stretch properties to reduce resistance during high-speed maneuvers. This feature allowed for smoother and more responsive control inputs. Additionally, a flexible elevator control torque tube was implemented, further refining the system by minimizing rigidity and improving the aircraft's overall responsiveness. To complement these improvements, the ailerons were optimized to deliver balanced and precise responses, ensuring the Zero remained agile and effective across a wide range of speeds. The control system exhibited unique characteristics at different speed ranges. At speeds below 288 knots at 4,500 meters, the aircraft maintained optimal control response. However, above this threshold, the ailerons experienced increased stiffness, affecting the aircraft's handling characteristics. The Japanese Zero engine integration with control systems required careful consideration of power effects on handling. The engineering team developed specialized mounting techniques to minimize engine vibration effects on control surfaces. This integration approach maintained the Zero's exceptional low-speed maneuverability while managing the challenges of high-speed flight. The control system optimization faced particular challenges in roll performance. Testing revealed asymmetric roll rates, with the aircraft demonstrating different capabilities when rolling left versus right. Engineers addressed these characteristics through careful adjustment of control surface geometry and mechanical advantage ratios. The Zero's instrument panel exemplified efficient systems integration, described as a marvel of simplicity that eliminated unnecessary distractions for the pilot. This streamlined approach to cockpit design reflected the Japanese philosophy of prioritizing essential combat functionality over comprehensive instrumentation. Engineering limitations and compromises. Despite its remarkable achievements, the Japanese Zero fighter revealed significant engineering compromises that would ultimately impact its combat effectiveness. These limitations stemmed from fundamental design decisions that prioritized performance over protection. The A6M Zero's design prioritized lightweight construction to achieve exceptional agility and extended range, but this emphasis introduced significant vulnerabilities to its airframe. Weighing approximately 2,360 kilograms, 5,200 pounds, when fully loaded, the Zero was markedly lighter than many of its contemporaries, such as the F4F Wildcat, which weighed 1,260 kilograms, 2,780 pounds, more. This dramatic weight reduction came at the expense of structural integrity and pilot protection, creating critical weaknesses in combat. The absence of armor for the pilot, engine, and other vital systems left the Zero highly susceptible to enemy fire, while the lack of self-sealing fuel tanks significantly increased its vulnerability to fires and explosions. Minimal structural reinforcement in critical areas compounded these risks, making the aircraft prone to severe damage when hit. Although the decision to construct the fuselage and wings as a single integrated piece enhanced maneuverability and structural soundness, this method complicated repairs and maintenance in combat environments, as it was more time-intensive than conventional designs. The Zero also faced notable performance limitations, particularly at higher speeds. Its control system, designed to prevent wing failure, stiffened significantly above 348 kilometers per hour, 216 miles per hour. While effective at preserving the structural integrity of the aircraft, this characteristic restricted its combat effectiveness against faster Allied fighters. Below 320 kilometers per hour, 199 miles per hour, the Zero's controls were exceptionally light, providing the agility for which it was renowned. However, in high-speed dives or fast-paced engagements, the stiffened controls severely hindered maneuverability, placing it at a disadvantage in encounters where speed and quick reaction were critical. The aircraft's engine installation further illustrated the challenges of balancing performance and practicality. The compact engine cowling, while aerodynamically efficient, occasionally struggled with heat management during extended high-power operations. This limitation became particularly evident in extreme conditions, where cooling inefficiencies could affect the Zero's overall performance. Underlying these issues was a design philosophy that prioritized offensive capabilities over defensive measures. The absence of armor plating and self-sealing tanks reduced weight, enabling superior range and agility, but left the aircraft exceptionally vulnerable to enemy fire. Similarly, the control system eschewed hydraulic boosting to improve mechanical reliability and responsiveness at lower speeds, a trade-off that severely restricted maneuverability at higher velocities. Finally, the single-piece construction of the fuselage and wings enhanced the aircraft's strength and aerodynamics but added complexity to production and field repairs, complicating logistics during prolonged combat operations. By 1944, these engineering compromises had become increasingly problematic. The Zero had fallen behind Allied fighters in both durability and speed, marking it as outdated for modern air combat. The aircraft's low never-exceed speed VN particularly hampered its effectiveness in diving attacks or escape maneuvers. The radio communication system presented another significant limitation. Poor shielding from ignition wiring and inadequate bonding of airframe components resulted in unreliable communications. This technical shortcoming often forced pilots to rely on visual signals during combat operations, compromising tactical coordination. The engineering team's focus on offensive capabilities aligned with Japanese naval doctrine, but proved increasingly problematic as the war progressed. While the Zero maintained its exceptional low-speed maneuverability, its inability to absorb battle damage or match the speed of newer Allied fighters highlighted the consequences of its fundamental design compromises. The Mitsubishi A6M Zero stands as a testament to Japanese engineering ingenuity during World War II. Through groundbreaking lightweight construction, revolutionary materials like extra superduralumin, and sophisticated aerodynamic design, the Zero achieved performance metrics that seemed impossible for its era. The aircraft's remarkable 12-to-1 kill ratio during early war operations validated its innovative engineering approach. Although the Mitsubishi A6M Zero was discontinued after World War II, do you think that, with its strengths, if it were to return to the sky with new features added, would this fighter become invincible? Please share your opinion in the video comments section. If you like this video, please give us a like. Thank you for watching.